This is the second of a two-part introduction video lecture dealing with linear horizontal motion. In the previous lecture, I presented to you and discussed the three basic equations dealing with linear horizontal motion. Before I show you those equations again, I'll remind you of vocabulary terms that you need to memorize. X marks the position of the object moving along the x-axis. It's the x-coordinate. It's called the displacement. Displacement being the amount by which an object's position has changed, measured in meters. V bar is the average velocity, measured in meters per second. V zero, or V naught, as we say, is the initial velocity, measured in meters per second. V, unsubscripted, is the final velocity. And A is the acceleration, measured in meters per second, or we say meters per second squared. One may combine two out of these three equations, if not all three of them, to create what we call a derived equation that is derivative of, or derivative from, or derived from these basic ideas. These two new equations prove very handy, save a lot of time in marching through sometimes complex problems involving motion. The first equation is derived in the notes. I won't go over that here. I'll just show you what it is and give an example of its use. We'll call the first three equations, equations 1, 2, and 3. This is equation 4. And there it is. X equals V naught t plus 1/2 at squared. An example of its use. Suppose V naught is 16 meters per second, and the acceleration is 4 meters per second. Let me repair this equation somewhat. That's V naught. And further, suppose we're asking the following question. How much time needs to go by before the displacement of the particle of the object is 400 meters? Well, we substitute x as 400, and you can see the rest of the substitutions here. We have a quadratic equation. The quadratic equation is an equation in which the variable of interest is raised to a power no higher than 2, or exactly 2. And that's the case here. Quadratic equations have two solutions. One is rejectable and is rejected, and the other is a physically meaningful one. Solving this equation, you will get a positive value for t, which is a physically meaningful answer, and a worthless and negative value that is cast aside. The fifth and final important equation dealing with linear horizontal motion, equation number 5 is shown here. The square of the later velocity equals the square of the initial velocity, and plus twice of the acceleration times x. Don't try to make sense of any of the terms of this equation, but it is a useful tool. We'll use it a number of times. As an example, suppose the acceleration of an object is known to be 5 meters per second squared, and we're told that the later velocity is 62 meters per second at a time when displacement has become 100 meters. We wish to know what the initial velocity must have been. We solve this equation for V naught. We substitute for V, 62, it's squared, unknown V naught squared, plus 2ax, 2 times 5 times 100. And it's a simple matter to solve this for V naught. I did it, and I get 53.33. I recommend that you keep close at hand these equations when you're solving problems involving linear horizontal motion. They would be on your equation sheet, along with many other equations of value to you that you will create for yourselves. Now, I say that you will create these equations for yourself, assuming that this class is going to be taught online in the fall of 2020, in which case your exams will all be open book, which means you can use any resource whatsoever to solve the problems on your exams. Any resource except another person. When we next meet, video lecture 3 will deal with the same sort of motion, except not on the horizontal line, but on a vertical line. We'll talk about vertical motion, in which objects are rising and perhaps later falling. Well, that's it for now. I hope you got something out of this lecture.